In this section of the course, we're going to look at how to use eigenvectors, eigenbases, eigenspace, eigenvalues, and all of this to be able to do algebra of matrices more easily. More precisely, we want to know when a matrix is close to being diagonalized. Alright, so let's start. I'm going to start with one n by n matrix, and I'll take a second one and call it B. We'll call A and B similar. If there exists a matrix P that moves one to the other. So if there exists an invertible matrix P so that I want to write B is P inverse AP. And we'll say that A is diagonalizable if it is similar to some matrix which happens to be diagonal. So all entries are 0 except on the diagonal where you have a non-zero. So A is diagonalizable if it is similar to a diagonal matrix. Alright, so let me spell it out because that's really the one we're going to care about the most this section. This one is interesting as well, but we'll work on this one throughout, trying to figure out when it's possible, when it isn't. So that means D is diagonal, so that means I have D11 and then zeros. I have D22 and then zeros, and I have D and N. Alright, so the only non-zero entries of D are on the diagonal. And I also need P. That P transforms one into the other, and an invertible matrix P so that, let me make sure I'm writing it the right way. Yeah, let's write it like this. So D equals P inverse AP. Alright, so a few facts about similar matrices. But before that, let me just say, we'll see it in the next example. But before we do an example, I just want to say that I want you guys to think of P as a change of basis matrix. So P is in some way a change of basis matrix. So A and B really represent the same linear transformation, just in a different basis. So in one basis, t would be represented by A, in the other, t would be represented by B. So that means A and B have a lot in common. So let's try to list a few things that A and B, if they're similar matrices, that they would have in common. Is it a theorem? That sounds a bit strong. Yeah, proposition, that's what I thought. Alright, so let's start with two similar matrices. Alright, first thing, let me make sure I'm getting them in the right order, so let me take my notes that you have as well. So, first thing, if A is invertible, then B is invertible. A is invertible if and only if B is invertible. Second thing is they have a lot of the same invariants. So the determinant of A is the same as the determinant of B. The rank of A is the same as the rank of B. Same thing for the nullity. And these make sense because if you remember, these tell us something about the linear transformation. So this is the number of dimension in its image, in its range. This is the dimension in its kernel. That shouldn't depend on what basis you take, right? It's just about if it's a plane, if it's a line, what does it look like? All right, what else? Oh yeah, characteristic polynomial, same. All right, same characteristic polynomial, that means same eigenvalues. But A and B will not have the same eigenvectors in general. Pretty straightforward to prove. Let me prove this one. That's the most interesting one, I think. So P, let's assume they're similar. So assume B equals P inverse AP. And then I want to look at the characteristic polynomial of B and show that it's the same as the one of A, or I could go the other way. It's really the same proof. So let's take PB of X. We know that that's the determinant of B minus Xi. So let me replace B by P inverse AP. And just so I can factor factor P inverse and P from this, I'm going to write the identity as P inverse P. So I have the matrix P on the left, so I'm going to be able to factor that. I have the matrix P inverse on the, P on the right, P inverse on the left. This is just a real number, well, a variable that represents a real number, so that the matrix can move past it. And then, because I'm factoring all the matrices out, I'm going to need I to reappear here. Alright, so this is good. It's good because I have exactly what I want here, A minus xi. I just need to figure out what to do with P inverse and P. Any ideas? Yeah, I should use the properties of determinant. I can split a determinant out of product. So I'll get determinant of P inverse, determinant of A minus xi, determinant of P, and then the last property I need is that the determinant of P inverse is 1 over determinant of P. Remember, these are numbers. Determinant of A minus xi, determinant of P. This cancels with this, and I'm left which is PA of x. Alright, so you can imagine how the first one would work. This is straightforward, this follows. The only one that's a bit more challenging is this one, but I think we've done enough. So let's stop right here.